Oops, now I'm taking a video of myself. Hi guys, today we are finally getting to the last note here about our algorithm for curve sketching. Okay, so this is going to tell you everything you need to know to create a good sketch of most functions. Okay, and usually, unless I've changed things, my test for this unit is just 4 curves you have to sketch: a polynomial, a rational, and then 2 weird ones that you won't really have any concept of what they look like until you do your analysis. Okay, so this algorithm is important for you to understand. And the way that I have broken it down is just into basically the 3 different things you need to look at: the original function, how you analyze it, the first derivative, and the second derivative. So if you want to just pause the video, you can copy all this right away, or you can copy it as I blab on. That's up to you guys. So first, you're just going to look at the actual function itself. Ask yourself, what kind of function is this? What do I know about it? Don't be afraid to use knowledge that you already have. So if you know it's a backwards facing cubic or whatever, So then you want to determine the domain and any discontinuities right away. So any vertical asymptotes, horizontal asymptotes, those are all determined using the original function, okay? The intercept, super important. That's the original function. And like I said, any asymptotes. And then the behavior around those asymptotes. The first derivative can be used to find the critical numbers. Remember, critical numbers can be places where the derivative is 0. So that means you have a local max, a local min, or a horizontal tangent, or where the derivative is undefined. So that is a cusp or a vertical tangent if it's undefined, but still the function is defined at that point. And if neither the derivative nor the function are defined at that point, that's a vertical asymptote, which you already would have found in step 1. Then you can determine where the function is increasing or decreasing. Sometimes this is necessary, sometimes it isn't, but if you need to know that, that is determined by using the first derivative. Then, if you want to use the first derivative test, you can use that to find the nature of the critical points. Okay, the second derivative is useful for finding where the curve is concave up versus concave down. You can also find any points of inflection, and then the nature of those critical points that you found from the first derivative, you could find them using the second derivative test instead of the first derivative test. Okay, so the amount of information that you need, you have to use some critical thinking to determine what tests you're going to use. So then you need to calculate either as you go or at the end all the y values of all those special x values that you found so you can label them properly. And then you sketch. Okay, of course, as always, if this doesn't give you enough information or you just want to be more comfortable, you can just make a table of values, okay? Just throw in some x values into your function to kind of fill in the gaps of where you'd like to just make it a better shape. But when I am looking at how you sketch and all of your analysis, I am looking at your knowledge of how to use calculus to analyze the behavior of functions. That's really important. That's why you're learning this. Let's be honest, we have graphing technology. We can easily sketch curves using a myriad of different choices of graphing technology. The reason why we still learn this, though, is because understanding the behavior of a function is still a crucial part of understanding what functions do and how they behave. Okay, so let's go ahead and use our algorithm now to just do these 2 examples. Okay, so we have a polynomial and a rational example. So first of all, like I said, you can take a look at what you know. Like, this is a backwards facing cubic. You can think about that. So it's going to have the general shape of this. We know that going into it. There's nothing wrong with thinking around that, but we need to show some calculus support to back up the actual shape of it. So we can say that the domain is any real number. There's no discontinuities because there's no discontinuities. Okay, the y-intercept is 0, 0. That's pretty easy to see. But are there any other x-intercepts? Well, to do that, we can take this function and set it equal to 0. So let's factor out the common factor of x right away. Okay, and then we can actually divide out this negative. Okay, so you can take the negative out. I did something wrong there. 2x minus 3x squared. There we go, and that's a 2x. Okay, we can take this negative out and put it in front of the x and then divide everything by that. So we can basically just divide a negative out of that bracket to make it easier to factor. Okay, because you're setting it equal to 0, you can just divide it out. So then that factors to x, 3x plus 5, x minus 1. So our x-intercepts are 0, negative 5/3, and positive 1. Those are the x-intercepts. Okay, so we did that. Okay, so that's kind of our usefulness of the first derivative. So we can actually already go down and put those in. So there's one of our x-intercepts. Negative 5/3 is about here, and then 1 is about there. Okay. So now we can go ahead and find the first derivative. Okay, so that is, where is it here? Minus 9x squared minus 4x plus 5. Okay, so now we want to find the critical points. So those are the points which make the first derivative equal to 0. So we can set it equal to 0. And again, we can common factor out a negative, divide everything by a negative 1, in other words, and that makes it easier to factor. So remember, if factoring this doesn't seem like a good time to you, you can use the quadratic formula. But either way, we get to x equals 5/9, and x equals negative 1. So these are our possible local max or min. Okay, we're guessing that there's going to be a min and then a max based on the fact that we know it's a backwards cubic. So this is where you need to decide, is doing the first derivative test useful at this point? So the first derivative test would allow us to look before and after this to see the behavior of the function. But in this case, I'm going to say that that is not a good use of my time because the second derivative is not hard to find. We want to find the point of inflection anyways. And now we can use the second derivative test to find the nature of these critical points, if they're maxes or mins, without having to do extra work of the first derivative test. So in general, my recommendation is with polynomials that you just go straight to the second derivative. So this is our second derivative. So we want to set it equal to 0. So we can take out a negative 2, 9x plus 2 equals 0. So then we solve this and we get x equals negative 2/9. So that is a possible point of inflection. So now we want to go and do the second derivative test to determine which case we're working with here. So we look at x less, that did not do what I wanted it to do. Oh, I don't know what's going on. Okay, but we look at x less than minus 2/9, and then we analyze the second derivative. Okay, so for points less than minus 2/9, we get that the second derivative is positive. So the curve is concave up in that section, which is what we predicted from the knowledge of it being a backwards cubic. And then the second derivative after minus 2/9 is negative. Okay, if you put in something bigger than minus 2/9 here, you get a negative answer. So there, that means it's concave down. So that means at x equals minus 2/9, that is a point of inflection. Okay, now we also can analyze our what is going on at 5/9. So 5/9 is greater than minus 2/9. So 5/9, and if you put it in, the y value is about 1.6. That is a local max because it's in the concave down section. And we can also determine that negative 1 and then its y value is negative 4. That's a local min because it's in the concave up section. Okay, so that is basically enough to draw a cubic, because now we can draw -1, -4 as our local minimum, and 5/9, 1.6, which is about here, as our local maximum. And then we know our point of inflection is -2/9, and you can find the y value for that right over here. Okay, so again, you can draw from the point of inflection up and back down again. And remember, that's going to go rather quickly. It's going to follow that. So don't like all of a sudden make it angle way out here. It's going to go up and back down. And then this is going to go down and then up quite steeply. And you can do this a lot better not on a trackpad. Again, if you're not comfortable with how steep that is, you can put in -3. You'll see it's way off the map. So there you go. That is and then you would label all your points. It's a somewhat decent sketch of that. Okay, so now let's get to the analysis of a rational function, which is a bit more complicated. All right, so we need to take a look at our original function and make some determinations about the intercepts and all that stuff. So first of all, let's factor this. Oops, okay, it went over here. It's a bit thicker. Okay, so if we factor this, we get x -2, x + 1. So no holes, but we do have 2 vertical asymptotes. So the vertical asymptotes are x is 2 and -1. So then the domain is x such that x cannot equal -1 or 2, but it's in a set of all real numbers. Okay, so we've determined that. So now let's take a look at the x-intercept. So the x-intercept is when we set the function equal to 0. So then we would get 4, 0. Okay, basically just setting the numerator to 0. And the y-intercept is when we sub x in as 0. So you'd get -4 over -2, which is +2. So our x-intercept is 4, 0, and our y-intercept is 0, 2. So we can actually already put those in. Okay, and if we go back over here, we can pick a different color and put in our vertical asymptotes at 2. Super bad here, x equals 2, and then x equals -1. So I like to kind of sketch as I go, because that gives me a concept of how much more information I need to get a good sketch here. All right, so this is the thing. So just take a look at what the question's asking you. If it asks you that you explicitly need to determine the behavior near the asymptotes, then do that. But finding where the sections are concave up or concave down will also allow you to do that. So you kind of have to decide at this point what is needed, if you actually need to do the limit work or not. So I'm going to skip it because I don't want to do it if I don't have to, and I'm going to see what else I can do here. So I also know that my horizontal asymptote is y equals 0 because it's a bottom heavy function. Again, if it asks you to prove that, you can just do the limit as x approaches infinity remember you take out the x, so then you're left with 1 minus 4 over x, and take out your x squared down here, 1 minus 1 over x minus 2 over x squared. Okay, these two x's cross off, so you're left with 1 minus 4 over x, all over x, 1 minus 1 over x minus 2 over x squared. Okay, these go to 0 to 0 to 0. Oh, shoot, the limit statement here. Okay, so then you're left with the limit as x goes to infinity of just 1 over x, which is 0. Okay, so that's how you know that the horizontal asymptote is y equals 0. So we can label that on our sketch as well. So interesting, we have a horizontal asymptote of 0, but we still cross 0 here. That's fine. We didn't do anything wrong. Remember, you can cross horizontal asymptotes. Okay, so now we want to go through and check out the first derivative. Okay, because we did everything we need to do with the function. All right, so this is going to be really fun, I promise. So it's the bottom, x squared minus x minus 2 times the derivative of the top, which is just 1, minus the top, x minus 4 times the derivative of the bottom, 2x minus 1, all over the bottom squared. Okay, so if we expand this and collect like terms, we get negative x squared plus 8x minus 6 all over bracket x squared minus x minus 2 all squared. So that is the first derivative. So now we have to solve f prime at x equals 0. Not fun, but we can solve that because guess what? Solving that just means solving for the numerator equaling 0. So we can just use quadratic formula on the numerator. Okay, so that's what we do. So x is negative b plus or minus the square root of b squared minus 4ac over 2a. And when we do that, we get x equals 0.8 and x equals 7.2. So those are our two critical numbers. So they could be local maxes or local mins. By the way, I went on to find out what their y values are just because we will need them. So it's 0.8, 1.5 and 7.2, and its y value is 0.1. So we can plot those right away. We just need to figure out what's going on either side of them. So 0.8 is about here at 1.5. And then 7.2 and 0.1 is about there. So at this point, we could find the second derivative and look at concavity. But the second derivative of that, no thank you. I do not want to do that. So I'm just going to use the first derivative test to figure out what's going on and hope that that gives me enough information. Okay, so the first derivative test, remember, just requires that you look on either side of the critical points. So I'm going to look first at less than -1 to see what's going on with the function in this section. Because right now I have no idea what's going on over here. Let's just say -1. So I want to know if the function is increasing or decreasing there. Okay, so then I'm also going to look between -1 and my first critical point of 0.8. Okay, then I'm going to look between 0.8 and 2, so my next asymptote. And then I'm going to look between 2 and 7.2. And then I'm going to look after 7.2. So basically, I have this humongous chart of intervals that I'm going to examine just the sign of the first derivative. So if it's positive or negative in each of these intervals. So I'm not going to take the time to actually go through and do those calculations. You can pause, you are perfectly capable of doing this. You can pause the video and try it. So you're just, one option is to just logically think through. First of all, hint, the denominator will always be positive. So really you only have to look at the numerator because the bottom is always all quantity squared. So the denominator is always positive. So really you just have to look at if the top is positive or negative in each of these intervals. So you can either just test actual points that fall within these intervals, or you can just kind of think logically. But I will tell you that here this is negative. Here this is negative. This is the first derivative I'm looking at, okay? Here it's the first derivative is positive. Here the first derivative is positive, and here the first derivative is negative. So that tells us that the function is decreasing, decreasing, increasing, increasing and decreasing here. So that means that 0.8 is going from decreasing to increasing. So that means x equals 0.8. That's a local min. Okay, and here our 7.2 is a local max because it's going from increasing to decreasing. Okay, so what does that mean? So this section here, notice it doesn't cross this axis at all. We know that, and we know that it's decreasing. So if you want to find a few points in there, you can. But basically, this section looks like this. Okay, so if you're unsure of if it should be here or up here, honestly, all you have to do is find 1 or 2 points, and you'll see that they're in that area. Or you can analyze how the function is approaching this asymptote. Okay, so you might have to do a bit more work than what I actually showed you to figure out the behavior there. In this section, we just determined that this is a local minimum. Okay, and we also know that this can't be approaching the asymptote here because it doesn't cross this axis. So we can reason, and we know it's increasing after this point. So we know that it has to go back up and look like that. And then this is something we don't know though. Actually, yes, we do. Because we know that between 2 and 7.2, yeah, between 2 and 7.2, the function is increasing. So between here and here, the function's increasing. So it has to be coming from here and then going up to here. And this is actually a local max. Isn't that funny that that's a max? And then it goes down barely at all and will approach its asymptote from above. Again, we know that because we know it doesn't cross the axis again, so it has to approach the asymptote from above. Now, this is an example here in this area that, to be honest, if I were doing this on my own and it was for a test, I like being really thorough. So this area and here, I would put in maybe 3 into the function to see where that hit because I don't like how sloppy that looks. And if I wasn't on a trackpad, I would for sure put 3 into the function and see what happens there. Okay, guys, so hopefully that gave you a good enough idea about how to use calculus to sketch curves. This was a polynomial and a rational, but you're going to see lots of different types of curves. And honestly, it's kind of, it feels powerful and kind of fun to be able to figure this much out without having to guess or use a table of values. So try to have fun with it. And yeah, thanks for watching. Hope you learned lots.